Hello, Calculus 2. We are working on area in polar coordinates finally. This is the last section, 10.5 in our textbook. There is a section 10.6, but we're not going to make it there. Those are Kepler's laws about the motions of the planet. Those are pretty cool. You could read that yourself. But here we go, area in polar coordinates. So you know what we do? We start with this basic formula, which is probably very unfamiliar. It's called the area of a sector of a circle. So from geometry, if I want the area of a sector of a circle, and a sector is defined from the center out, a certain radius, a sector is some included angle theta, then I can find the area of that sector of a circle with this formula, 1/2 r squared theta. Of course, when you use a formula like this, theta better be in radians. Yeah, that might be unfamiliar to you, probably is, but it's true. It's a geometric formula. Let's just check it. What if I wanted the area of the whole circle? Then the theta would be 2 pi. And so let's just see how that works. If this is 1/2 r squared and theta was 2 pi, because I wanted the area of the entire circle, the 2's cancel, and I get pi r squared, which is the area of the entire circle. So that worked nice. So we need this formula because in polar coordinates, when I want area in polar coordinates, if I've got some function out here in polar coordinates, r is a function of theta, then I'm not working rectangularly. I'm not going to add up rectangles. I don't have a height y. I don't have a dx. Instead, I'm adding up sectors of a circle. So I sweep out sectors of a circle. Now you may say, wait a minute, that's not a circle. Well, you're right. Remember we used to, the rectangles we used to add up didn't really used to be rectangles either. They were, the top was some curve, and then so this is some curve, but what we approximate it as, we pretend this is the center, we pretend that's r, and this is a little d theta. And we approximate that as a sector of a circle, and we add all those up as we move around this way. So I'm adding up sectors of area. So the formula for area in polar coordinates is this. It's an integral. We add all those up. There is a 1/2 out front. We go from alpha to beta. We go from some angle to some other angle. We work with respect to theta. We're going to do this with respect to theta. And we are integrating, that's our little d theta. And we are integrating the function squared, the r squared. So r is f of theta, so it's f of theta squared. So, that's cool. You know, I wanted to explain that to you. I mean, this is the new magic formula for area in polar coordinates. But it comes from this idea. It comes from adding up sectors of approximated circles. Yeah. So that's it. And so let's try a problem. So that's the little background there. It's not much to that. There's all kinds of good problems where they have little twists and turns. So here's one I like to do. It says, I make up this one, and then I give you an assignment with similar problems. Probably the homework's got a lot of good ones. This says find the area of a, what did I make up here? 3-petaled rose with petals length 4. So what I did? Yeah, with petals length 4. Well, anyway, so in other words, I don't know, I could have given you the equation, but I thought maybe you would know this equation, or you could look up this equation. Or you're supposed to know this equation. So I remember this a little bit. These roses, we've been talking about these special polar graphs. There isn't too many. There's the limicons, there's the roses, the circles. There was a lemniscate. That was beautiful. Hang on. There's a lemniscate, which was like the symbol of infinity. I never did talk about that, but you can read your book. You can read your book. You don't need me for everything. But anyway, I need the equation of a 3-petaled rose with petals of length 4. Let me think. Oh yeah, when it was a three-petaled rose, when it was an odd-petaled rose, this number was odd. So there it is. There's one. By the way, I could have done sine 3 theta. That's also a three-petaled rose. And by putting a 4 there, that's petals of length 4. So this is the equation, and maybe I want to draw a picture of it. I've done this guy before. It's petals of length 4. I think when I plot points, he comes like this. Now, by the way, your graphing calculator works. I guess I've tried to tell you that, but maybe I haven't. The graphing calculator in polar mode, you go to polar mode in your graphing calculator. You go to mode instead of function mode where you've been all your life. There's parametric mode where we were last week, and then there's polar mode. And then when you hit y equals, it's r equals. When you hit the variable x, you get the variable theta. So graphing calculator has that ability, so that would help. But there it is. Last video I was talking about finding the tangents at the pole. I mean, if I want the area of this rose, maybe I want to do one petal and multiply by 3, or maybe I want to do half a petal and multiply by 6. But if I do, then I need to kind of know what's called these tangents at the pole. When does this petal come into the pole? So I could set this equal to 0. I could work hard on all that. Let me try that a second. If I set this equal to 0, divide by 4, cosine 3 theta. Let's see, when does cosine equal 0? Pi over 2. Right? Cosine equals 0, pi over 2, yeah, that's right. And several other places. Negative pi over 2, and 3 pi over 2, and 5 pi over 2, and 7 pi over 2. I mean, I can list a lot of places. And in fact, when I'm dealing with a tripled angle, I've been trained to list 3 revolutions worth of answers. Because this is the answer for theta. This is the angle 3 theta, and when I want theta, I end up dividing by 3. So the answer is pi over 6, and that's this one. But if I was going to try to list all of them, there would be another one there. Actually, there's one there, there's one there, there's one there, there's one there. This one's negative pi over 6, I guess. So I guess I could set up an integral to get the area of, like I said, this one petal. There's a lot of options, you guys, on how to do this. You could go get this one petal. What am I doing? I'm going from negative pi over 6 to pi over 6. I'm going to take this function and square it. And there's a half out front. Oh, and I'm only doing one petal, so I guess I should multiply by 3. So that works. Here's what else works. What did I say? I said, let's do half a petal. That's probably kind of smart. It's smart to work that 0 into the problem. Let's just go from 0 to pi over 6. 0 to pi over 6. I'm sweeping out sectors of area. Remember, you don't have to remember, but it helps you think. What you're doing is from the pole, you're sweeping out they're not rectangles, they're little sectors of area that you're sweeping out. From 0 to pi over 6, you're adding them all up. That would work. There's a half out front, and then that's just half a petal. If I'm only doing half a petal, then multiply by 6. Is that what I'm doing? Multiply by 6 to get all of it. So I taught you all that, and I did all that work, and I should do one of these integrals. We should find this area. But the truth is, I want to show you something. There's a better way to do this problem. I'm just going to go up top here. It's cool. We analyzed the hell out of it. It was cool. But I happen to know this, and I think I've said it before, that in order to sweep out a full 3-petaled rose, when it's an odd-petaled rose, you only need 0 to pi. And here it is going from 0 to pi over 6. That's that half a petal. When it goes from pi over 6 to pi over 2, I think it gets this other petal over here. And when it goes from pi over 2 over to here, it gets this pedal. And when it finishes here from 5 pi over 6 to pi, it's getting this pedal. Anyway, an odd pedaled rose doesn't need 0 to 2 pi. 0 to pi plots it out. And I've said that before, and it's important to know. And so I don't have to do half a pedal or one pedal and multiply. I could just go 0 to pi. I think that's smart. I think that's smart. Just do the whole thing. I just overanalyzed it just for fun. Let's go ahead and do this problem. It's been a while since we've integrated. It might have been a while since, but what happens is these got sines and cosines, of course, and when you square them, of course, you might have to recall a few things. That's going to be a 16 cosine squared 3 theta. The 16 can come out. That's an 8. And it's a cosine squared 3 theta. I remember how to do cosine squared. In chapter 8, I learned that there's only one way to do cosine squared. You do the half angle formula. You turn it into 1/2, 1 plus cosine, and then you double that angle, 6 theta. And I haven't integrated yet. I have not integrated yet. That's just me using the half angle formula. I think I did that right. You guys should remember that. And now I think I'll integrate. The 1/2 can come out. That'll now be a 4. I'll integrate the 1. That's a theta. I'll integrate the cos 6 theta. I think that's a sine 6 theta. But it spits out a 1/6. And we're finished from 0 to pi. What's fun about this is you plug in the pi and you get 4 pi. And when you plug the pi in there, the sine of 6 pi is a 0. And you plug the 0 in, and that's a 0, and the sine of 0 is a 0. So we get a bunch of zeros here. And my answer is 4 pi. That's interesting. I didn't do anything wrong, did I? 4 pi for that 3-petaled rose. That's interesting. Petals of length 4. Huh. Anyway, that is interesting. So there's plenty more problems. I'm going to hit pause and we'll try some other stuff here. Do some homework.